5th time I've done this. Same thing. Same exact thing. E times dA cosine theta equals little r cubed over big R cubed times Q over epsilon naught. This is Gauss's law for this problem. Now you don't want to get the r's mixed up. The little r is the r that's associated with our Gaussian sphere. Now that could be any value we want, as long as it's less than big R. And it is every value, because we're writing it as a function of R. So just imagine this to be a flexible, like balloon that you inflate and deflate to get all the different electric field intensities at all the different R's. So this just gives us E times 4 pi R squared equals little r cubed over big R cubed times Q over epsilon naught. And then we're going to get a factor of R squared. It's going to cancel. And we solve this for E. And this is typically what we do. We set up our Gaussian surface. We set the flux equal to the charge enclosed over epsilon naught. And then we solve for E. That's our procedure. So this is a technique for getting the electric field. So E then, when the R squareds are canceled, it's just going to be Q divided by 4 pi epsilon naught R cubed times R. It's going to look like that. And so the R value is variable. So what that's telling us is that the electric field is constant, has a constant slope, I should say, because it's constantly increasing for values of R that are less than big R. So this is E equals some constant times R, like this. So the constant then, the slope of this curve is this thing in the brackets. Q divided by 4 pi epsilon naught R cubed. That's the slope of that curve in that region. And it goes linearly as R. So that's kind of interesting then, because if you put a negative charge, let's say you had a hole going through this thing. If you put a negative charge up here, then the force would be minus some constant times R, and we'd have simple harmonic motion. That'd be like a Hooke's law. Okay. And the same thing would be true if you had the Earth and you dug a hole through the center. And you took a mass and you dropped it through. The gravitational force would be some constant times R with a minus sign on it. So this thing would speed up until it got to the center. You'd want to be going pretty fast here because the temperature at the center is similar to the surface temperature of the sun. And so you whip through this area, and then you come out on this side, and then all that kinetic energy is turned into potential energy. You've got simple harmonic motion, omega squared equal to K over M, where K is an equivalent constant for gravitational fields. If you dug the hole over here, then you would just have a component of this force, because the force is pulling inward. So you just have a component of the force, but it would be to a shorter distance. So the omega turns out would be the same. You know what the time it would take to go from here to there, or from here to there, or from here to there would be for the Earth? They'd be the same. And do you know how long that is? 17 minutes. It's called the 17-minute express. So you could dig a hole that went straight through like that. And if you're farther away, then you just have a small component of the force that's toward the center, but through a shorter distance. And so it ends up being the same period of oscillation. And so if you just dug a hole straight through, and then you got in there and you had a frictionless thing that could carry you to your final destination, you would get there in 17 minutes. It would be China, it would be straight through the center of the Earth, problematic. You want to, it's a good heat shield. You try to do that. But, the same thing would happen here with the charge. If this were a negative charge, there'd be an omega that would be equal to, well, this K would have a little q in it here, or the minus q. And it would just oscillate back and forth with simple harmonic motion. But then if you get outside of the sphere, then all of the charge is enclosed. It has spherical symmetry, so it just goes like kq over r squared outside of the sphere. So it's the same as if it were a point charge, or if we're talking about a mass, it's the same as if it were a point mass. And so this is the result that would have really interested Isaac Newton. Do this in basically one step using Gauss's law. So that means that the electric field at the center of the sphere would be 0. Because then you can think of it as an infinite number of other spherical shells that are surrounding it. You'd have no charge enclosed by the Gaussian surface. And similarly, if you were at the center of the Earth, because it's the same kind of inverse square gravitational problem, you'd be weightless at the center of the Earth. Any questions about that? Okay, there's two other kinds of charge symmetries that we've already examined in chapter 22, and I want to get to those today so that you can compare and contrast them to what we learned in chapter 22. And I do believe this will help you in the exam, because you can conceptualize what the electric field is doing in each of these cases. So we just looked at the spherical case. There's three types of problems that we look at with Gauss's law. One is the spherical case. We've done this. That's what we've been doing for the whole lecture. 2, the cylindrical case. And 3 is the planar case. So with the cylindrical case, all we need to do is assume an infinitely long cylinder. Otherwise, Gauss's law is not going to help us. It's just going to make things worse. Planar, here we also want an infinite plane. So if we don't have these idealized approximations, then it's not that we can't use Gauss's law, it's just that the integrals are going to be too gnarly, and we just go back to basic principles from chapter 22 and integrate k dq over r squared the way that we did before this lecture. Okay, so let's do this then for a line of charge. Now what we showed last time is for an infinite line of charge, first we had to integrate the little dq's, we got little de's, and then we had the d cosine theta, then we had a lambda dx, and then we did it about the midpoint. Do you remember all of that? And then we took the limit as the a value goes to infinity. And what we got was 2k lambda over r. That was the result. Now it was over x before because I had the thing pointed this way. We had this distance, we call it x. The only thing I'm changing here is that I'm making r not the spherical coordinates are, but the cylindrical coordinates are. Okay, so now we're in a different coordinate system. We have to use cylindrical coordinates. So in other words, this x, and this x, and this x, That's all r away from the z-axis. If this thing is infinite, it doesn't matter where you put this, because you're still integrating from minus infinity to plus infinity. So this was the result that we got when we took the limit as x, or in this case, r goes to infinity. So what I want to do is show that I get that result with all of that trig substitutions and figuring out different components and taking the limits as x or y goes to infinity. That was a lot of trouble. What if we can do this in one step? Well, here what we're going to want to do for a cylinder is construct a surface that surrounds the infinite line of charge. Okay, and so that's what we've done here. You go, well, you didn't do a very good job because the cylinder isn't infinitely long. You've only enclosed a little bit of the charge, not an infinite amount of it. True that. But we can say, well, that's all right. If I need to later, I can just take the limit of my expression as L goes to infinity. And then I should be good to go. Turns out I won't need to do that because L is going to cancel out of my equation. For something that has spherical symmetry, the electric field needs to point straight away. And so that's in this cylindrical coordinates r hat direction. So E then always points in the r hat direction. But not our spherical coordinates r hat. Very important that we distinguish between them. This is our cylindrical coordinates r hat. Which is going to be straight away from the line. Okay, so down here it'll be this way, out here it'll be that way, on the back side it'll be this way, etc. And then these end caps are going to be the end of our integration. And so the total flux then, what do we do in these problems? We write an expression for the total flux, then we set that equal to the charge enclosed over epsilon naught. So that's what we're going to do again. But now the total flux is the flux over three surfaces. We've got the flux over the end cap, but the electric field is always pointed this way, over the end cap. And similarly on this end cap, the electric field is always pointed perpendicular. Up here, the electric field would be pointed this way, but the unit normal is going to be perpendicular to it. So therefore, no electric field lines escape through the end caps, right? Because there's no flux. Remember we said before that if you don't expose any area, then you don't have any flux. It means no electric field lines get out this way. They all have to get out this way through the walls. So we'll set this up as psi total is psi over the left end cap plus psi over the right end cap plus psi over the walls. And the only one that's going to contribute is psi over the walls. Because remember, it's got to be a closed surface. So this closed surface means that we've got to trap all of the charge inside of the surface. And again, we haven't done that unless L goes to infinity, but we'll just wait to see whether we need to do that or not later. And plus psi over the walls. Okay, so since these are 0, is everybody clear as to why those are 0? So the the electric field is always pointing in the r hat direction. We showed that in chapter 22. It's also true if you turn this thing, has cylindrical symmetry, meaning the electric field pattern isn't going to change. If it was stronger on this side, weaker on that side, and you turn this thing, then that would change the field pattern, but you didn't change the symmetry a bit. It's still a cylinder or a line. You haven't changed. So that means the electric field has to be always in the r hat direction. There are more rigorous proofs for that, but that one I think is good enough. So here then, the electric field always points in the same direction as our unit normal to the surface, which is in the r hat direction. So we can write this then as the integral of E dot dA, or E times the integral of dA cosine 0 degrees. So this should look familiar. We've done this before quite a few times up to this point, because the electric field is constant over that cylindrical surface at a certain distance r away. The electric field is constant. So I'm pulling it outside, and then what's the integral of dA over a cylindrical wall that has a radius r and a length L? 2 pi r L. Let's see if that makes sense. Okay, so here's my cylindrical surface here. Here's r. So this distance, 2 pi r L. Everybody good with that? That's the area of the wall of the cylinder. So this is E times 2 pi r L. So you say, okay, well, is this when I said L equal to infinity? Well, no, not quite yet. So this has to equal the charge enclosed. Well, the charge enclosed is infinite. So let's not do it that way. The surface is also infinite, so maybe the L's can cancel if we do this right. Let's just do it for a finite L, and then if we need to, we'll take the limit as L goes to infinity. So lambda is equal to the charge that we enclose divided by L. That's just charge per unit length. And so therefore, the charge that we enclose is lambda L. Charge per unit length times the length. So I'm not going to put in Q here. Instead, I'm going to put in lambda L over epsilon naught. And so that's the great trick that keeps me from having to take the limit as L goes to infinity. Isn't that beautiful? The L's cancel. So I don't have to take the limit as L goes to infinity. So this gives me then E equals lambda over 2 pi epsilon naught r. Okay, well, let's see if that reduces to this. 2k lambda over r. But remember, k is 1 over 4 pi epsilon naught lambda over r. So that's just the 2 and the 4 cancel. That's just lambda over 2 pi epsilon naught r. It's just k over 2, basically. Or, I'm sorry, here, 2 times k. 2 times k lambda over r. 2k lambda over r. But k is 1 over 4 pi epsilon naught. So it's lambda over 2 pi epsilon naught r. Same thing as what I got here. So instead of doing all that nasty integration of all the different little charges, I've been able to do it in one step. One single step, and I'm done. Any questions about that? I think the sphere was a little easier to see, because here you've got to do the right substitution. And it kind of looks like this isn't infinite, and you're trying to enclose an infinite amount of charge. we use the trick that we just make it a certain length L, find the charge enclosed within that length L, and then if we had to, we would take the limit as L goes to infinity, but we didn't need to because the L's cancel. Now, if it weren't infinite, then this wouldn't be quite right. So this is still works, though, for a finite line charge. If the magnitude of R is much, much less than L. So in other words, if I'm out here somewhere, and this is my R, if that R value is way less than L, then I can use the semi-infinite approximation, and it'll still work. I might have 1 or 2% error, but I can use this idealized approximation for a finite line of charge as long as you're close to the charge, and reasonably close to the middle. And so when would we use this? Sounds kind of obscure. But we have things called cylindrical capacitors. In a cylindrical capacitor, you have a negative anode and a positive cathode that look like this. And so this is going to generate an electric field in between, and it's that electric field that stores electrical energy. So by being able to work with this, as long as the radius here of this thing, little r, is small in relationship to the length L, we can use the semi-infinite approximation, and we can get the energy stored in a capacitor. And so it's that kind of problem then that we'll get to. We have a whole chapter on capacitors later. But you'll need to understand this before we can apply it to those other applications. So each thing is built in on the previous one. Now what do you suppose would happen if we spread the charge out over a cylindrical shell instead of having it right at the center? How is that going to affect the electric field out here? It won't, because it has cylindrical symmetry, so the electric field will be just fine as long as R is greater than big R. Then E is still going to be lambda over 2 pi epsilon naught R, just using the same reasoning that we used before. When you're inside, you're not enclosing that charge, though. So inside, the electric field is going to be 0, because there's no charge enclosed. So the electric field for this is big R, it's going to be 0 to here, and it's going to drop off as lambda over 2 pi epsilon naught R. So it'll drop off as 1 over R for the electric field versus R. Instead of 1 over R squared, it'll drop off as 1 over R. But it'll be 0 in here. Electric field will be 0 up until R, and then it'll drop off as lambda over 2 pi epsilon naught R outside. So that means that if you had a cylindrical capacitor, you'd only have to worry about the charge that's inside of here, not the charge that's outside when you're calculating the electric field. So we'll get back to that later. Any questions about that one? Then finally, I'm just going to do this real quick, and then we'll pick up after the exam the rest of this. Remember, just one very simple problem. It's not going to involve you having to write Gauss's law out or any of that stuff for the exam. But this will be the first subject covered in detail for midterm number 3 and for the next quiz. And what I found is that people that don't get this end up messing up quite a few problems down the road because we use Gauss's law results over and over again through the rest of the semester. So it's really important that you get this now. Finally, we have an infinite plane of charge. Now remember before, we got the infinite plane of charge was 2 pi k sigma. That was a constant. How did we get that? In chapter 22, we took the electric field for a ring, and then we added up a bunch of rings to get the electric field for a disk, and then we took the limit as the radius goes to infinity to get the electric field for the plane. That's a lot of work. But here, I'll show you how to do it in one step using Gauss's law. You have an infinite plane of charge. We can do a setup here. Let's say it's a uniform distribution of charge on the surface. So sigma, that's our charge per unit area again. Or I'll call it Q over A. We can set up some little, what we call a Gaussian pillbox in here to enclose a certain amount of the charge of that sphere. And what our goal then is to find E using Gauss's law. Okay. So, for example, this could be 10 to the minus 5 coulombs per meter squared. That could be the charge density of this large plane. And so the surface that I'm going to draw is a pillbox. So it's kind of like an inverted cylinder. In a way, it's like the problem that we just did with the line of charge, but with the axis of the cylinder rotated by 90 degrees. And so we've already shown that the electric field points straight away, and because of the symmetry of the problem, it should be constant on the end caps. So E, if we're a certain distance away, it should be the same here as it is there, 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 because we have symmetry in the planar direction. Similarly, out in this direction, too. The electric field should be the same at any distance that's parallel distance away from the plane. Same thing up here. So we just set this up so that those two are equal distances above and below. This is the area of the pillbox, and this is the side. So the total flux is going to equal the flux over the top cap plus the flux over the bottom cap plus the flux over the walls. And now, in the cylinder case, it was the flux over the walls that contributed. But here, the flux over the walls is 0 because the unit normal is perpendicular to E. Over here, this is n half. E is going to point that way, either away in the positive above or down away below. So this is gone. But these two should have the same value because you have an equal number of electric field lines escaping this way as that way, but none can escape that way because they're all moving this way away from this charge. So they can't go this way. There's no component of the electric field that goes that way, so they can't escape that way. They can only escape this way or that way, and so we're setting up a perimeter to count those electric field lines and see how they're escaping. And so for the top wall then, it's just going to be EA for the top cap. For the bottom cap, it would be EA equals charge enclosed. Now in this case I'm going to make, because the charge is Q over A, I'm going to make charge enclosed equal to sigma times A. Before we were doing a one-dimensional charge, it was Q is equal to lambda L. But this is charge per unit length times the length. This is charge per unit area times an area. So the amount of charge that I'm enclosing in here is sigma A, where A is the area of that. And that's also the area here, A, and that's also the area there, A. So I can rewrite this then as Q enclosed is sigma A over epsilon naught. So that's my charge enclosed. And so now I can say, okay, well, the same argument as before. If I need to, I can take the limit as A goes to infinity, but I'm not going to need to because the A's cancel. So when I cancel out the A's, I get 2E equals sigma over epsilon naught, or E equals sigma over 2 epsilon naught. Now, how does that relate to what we got before when we did it the long way? We got E is equal to 2 pi k sigma. So let's rewrite k as 1 over 4 pi epsilon naught times sigma. So that just gives us sigma over 2 epsilon naught. So we see that these two agree, and we did it in just one step using Gauss's law. Okay, so it shows it's a constant. It shows that it doesn't depend on the distance away from the plane. And this will work as long as your distance away is small in relationship, as long as this distance y is much, much less than a characteristic length of the plane A, L. So that's your semi-infinite approximation. And this gives us the same result that we obtained in chapter 22, but with a lot less work. Any questions? All right, so one concept question from this thing, but please don't forget about it. And then after the midterm this week, we'll do a lab that is kind of a combination of getting used to the equipment and also plotting up electric fields and using the concept of electric field. So good luck with the exam.